Hello, class. This is technically the first lecture of the second week. This is the mathematical treatment of measurement results. It is section 1.6 of the text. Let's get the slideshow. It is to explain the dimensional analysis, that is the label on the number, approach to mathematical calculations involving quantities. Use dimensional analysis to carry out unit conversions for a given property and computations involving two or more properties. So, this would be like saying to somebody, convert miles to kilometers. Now, under normal circumstances, for normal quantities, they share the same base value for 0. So 0 kilometers is the same as 0 miles. Temperature is different. For temperature, it's the zeros are shifted between the Celsius and the Fahrenheit scale, and it makes it a little more complicated. A quantity of interest may not be easy or even possible to measure directly, but instead must be calculated from other indirectly measured properties and appropriate mathematical relationships. So in this case, they're talking about something like density. The way you measure density is you measure mass and you measure volume and you divide the two. And then you have grams per volume. The mathematical approach we'll be using is known as dimensional analysis. Dimensional analysis is based on the premise that the units of the quantities must be subjected to the same mathematical operations as their associated numbers. So when you have 1 gram divided by 2 liters, the 1 and the 2 are divided and it's 1/2. And the grams and the liters are divided, so you have grams per liter, 1/2 gram per liter. So that's what dimensional analysis is. A conversion factor, or unit conversion factor, is a ratio of two equivalent quantities expressed with different measurement units. So the way you make a unit conversion factor is you take a true statement, in this case 2.54 centimeters equals 1 inch, and you divide both sides either by 1 inch or by 2.54 centimeters, and you get a value that a number, a quantity that has a value of 1, because anything that's the same value divided by itself is 1. So this is a unit conversion factor, and this is a unit conversion factor. And when this is applied to inches, you have inches here multiplied by that, the inches will cancel out, and you're left with centimeters. And also you could multiply this times quantity in centimeters, and the centimeters would cancel out and leave you with inches. So here's a whole bunch of true statements that you could use. I'll tell you, I found a true statement one time when I was driving across the border on the western edge of Alabama. It's coming into Alabama, they've got the miles and the kilometers both marked on the highway. And I noticed that the 8 kilometers and the 5 miles, the two signs were almost on top of each other. And I began to realize that's virtually the conversion factor to within many decimal places. It's 8 to 5. 8 kilometers divided by 5 miles is a unit conversion factor, or 5 miles divided by 8 kilometers is a unit conversion factor. So we must use the form of the conversion factors that results in the original unit canceling out, leaving only the sought unit. So we have 34 units, and then we multiply it by a unit conversion factor, in this case, one in which the inches will cancel out. They didn't actually put the line through the inch there, and you end up with 86 centimeters. Okay. And apparently, as far as these slides are concerned, that's all they're going to say about that. I'm going to make a supplemental lecture with working some examples of this. Okay, now we're going to talk about temperature. It's a war between Mr. Celsius and Mr. Fahrenheit. Mr. Fahrenheit, he knew somebody. Well, in both cases, the way temperature was taken back then was with a bottle of water that had a, and let me pull up something here, back up, escape. Let me go to paint, and let me erase everything. That's not going to work. File, new, don't save. Boom, there we go. Okay, so we've got Celsius and Fahrenheit. Celsius, that's not a good C, and Fahrenheit. Okay, so Fahrenheit knew somebody. Now let's get rid of the C. Okay, Fahrenheit knew somebody that, let's start with the shape of the thermometers back then. Back then they used air. I'm not going to be able to draw a tube very well. I should be able to draw a straight line. Okay. There we go. And then another straight line. And then we do free form around that. This is a cork, all black. And we got some water here. And this water is, let's give it a color. And let's see, let's fill it. Boom. Oh, that was no good. Take that back. Brush. All right. Color. All right. And fill it up to there. I should have extended this a little bit further up. Black. And put a meniscus in there. And then we, boom, red. Okay, so they would take this bottle with air and stick it in somebody's armpit and measure where the height of the liquid was. And they'd say that's temperature 1. And then they would move it to another thing, and they'd say, well, that's temperature 2. Well, Fahrenheit used human body temperature, and apparently he chose somebody hot. And it came out, and he called that 100. Human body temperature, he called 100 F. And he called salt, get that L in there, salt, ice, mixture, he called 0 F. This is like what you use to make ice cream with a crank ice cream maker. And he set the 100 degrees between the salt ice mixture and human body temperature, and that was the Fahrenheit scale. Celsius, on the other hand, he said boiling water. At sea level is equal to 100 C, and ice melting is 0 C. So they had the same concept, they just chose different standards. And then when you get to, so water in the Fahrenheit scale comes out at these weird temperatures, boiling at 212 and freezing at 32, because he did not base his scale on water. So 100 degrees C covers the same temperature interval as 180 degrees F. Now that's important in the equation for converting one to the other. Yep. That's not working. Okay. So now I got another story to tell you. Take those away. The other story I have to tell you, let's see if we can just get rid of all of this. New. Don't save. Is if you were to take this and you have the volume of gas. So you have a gas and a piston. So here's a cylinder with a piston. And another word for this, if you put a needle up there and plunger, something for you to push on here and your other fingers to push on here, you got a syringe. Yes, so think of this as air in a syringe. And now we have temperature. It doesn't matter the sample of gas. It turns out that all gases, at all samples of gases that you would have, with temperature, they get smaller as you go to lower temperatures until they get to their liquefaction temperature, and boom, they drop off. Okay, so this other one, maybe like hydrogen or helium, it goes way, way, way down before, boom, it liquefies. It may be something like nitrous oxide, which liquefies at a very high temperature. Boom, it liquefies. But what's funny about all of this is that if you extrapolate all these lines, they all go back to the same temperature, and this temperature is given a special name. This is the place that all gases extrapolate. They would extrapolate to 0 volume at this temperature, and we call it absolute zero. I'm going to have to improve my handwriting on this. Okay, so that's important. Let's go over here. So, based on that absolute zero and the size of the Celsius degree, they made the Kelvin scale. So the Kelvin scale has 0 at absolute zero. Now, since water freezes at minus 373 degrees Celsius, you turn that around and you say that it's 373.15 degrees Kelvin. This is the same as 0 degrees, I'm not going to get the superscript here, C. And water boils at this temperature, which is the same as 100 degrees C. So, so now we've talked about 3 temperature scales: the Kelvin scale, the Celsius scale, they've got degrees, same values, and we've got the Fahrenheit scale, which is sort of an outlier, but it's what America uses for its weather temperature. So only the United States uses the Fahrenheit scale. The rest of the world and science uses the Celsius scale or the Kelvin scale. Yep, that's not good. All right, so let's go back to this. Boom. Okay. I need to have a supplemental lecture on this, but this is how you convert from Fahrenheit to Celsius and from Celsius to Fahrenheit. Oh, I'm sorry. This is Fahrenheit to Celsius, and this is from Kelvin to Celsius. You take the since this is the value of the freezing of water, then you take your temperature Celsius and you add to that. Again, we're going to have a supplemental lecture on this because it is so important. But here are some highlights between Fahrenheit and Celsius, where Celsius is 0 and water freezes. Fahrenheit is 32 degrees. 37 degrees in Celsius is what we call body temperature on the body thermometer. Humans are all over the place in actual body temperature. And this reflects significant figures. There's only 2 significant figures there. But somebody ran it through, 37 through the calculation, and they came out with 98.6 as the human body temperature. And everyone takes that as gospel. But it only started with 2 significant figures. So the 3 significant figures in 98.6 are, they're not all significant. And this is one I like to catch people on is I'll say, you know, it's minus 40 degrees out there. And I'll ask them, I'll say, well, what's colder, minus 40 Celsius or minus 40 Fahrenheit? And I get answers all over the place before I tell them it's the same. And a strange coincidence, it's about minus 38 degrees Celsius, is the freezing point of Mercury. It's so very, very close to minus 40 Celsius. So these are things you need to know. We're going to go over, again, highlights along the scale. 25 degrees Celsius is the official laboratory temperature, which is 77 degrees Fahrenheit. Human body temperature is 37. 65 is where they pasteurize milk. Of course, 100 degrees Celsius is the boiling point of water. Anyway, that's what we're going to do. And that's not relevant. Thank you very much for listening. Bye-bye.